אלכס, אנחנו בשידור, נא להתחיל בבקשה. סליחה.
Well, we had a few technical challenges, and right now I believe that we have to continue the presentation of Doron from the last point that we left it. Can you please set it down?
אתה רוצה בסרטון שלו או שאתה רוצה לדבר איתו? סליחה.
אני רוצה את החלק האחרון של הסרטון שלו, בבקשה.
אוקיי, אין בעיה. אוקיי, בבקשה.
And you want to shift that repetition rate very fast from very high to very low, and you need your energy to be fixed. So one of the things you could do that is just control the current, and as the repetition rate goes down, you lower the current. Unfortunately, it's very difficult to change very high currents like 10 amps very fast, and also if you keep the current fixed and you go to very low repetition rates, usually the problem is ASE. When you start getting amplified spontaneous emission, just because you maintain a lot of inversion in the fiber, so as you go to very low frequency, there's a huge distance between the pulses, and this distance is just filled with a lot of pump, which generates, causes inversion in the fiber. And one of the problems with the high inversion is the fact that your ions start to drop. This is, in this example, it's erbium, but you can use the same example for ytterbium. And as you get a lot of spontaneous emission. And spontaneous emission is really noise. It's not pulse. It's broadband. You can't use it. And this is why, as you go to very low repetition rates, what you get is basically a lot of ASE. So in our design, what we tried to do is we went with a different technique, and this is called pulse pumping. And with the pulse pumping technique, we don't keep the current high or constant at low repetition rates. What we do is we pulse the pump and then we stop it. And in the pulsing of the pump charges the fiber. But when we stop the charging, we don't completely stop it because the fiber gets discharged, but we just maintain the inversion by keeping the current very, very low once the fiber is already charged. And this is what we call the biasing. So basically what the electronics here does in a very fast way is keeping the inversion level fixed while the repetition rate starts to modulate, but using not a changing current, which is a DC current, but using this scheme of pulse pumping where we are basically pumping for a very short time with a strong pump current, and then between the pulses, we only maintain a biasing current. And by doing that, what we are able to do is reduce the ASC level, especially at low currents, at low frequency, low pulse repetition rates. We can keep the ASC to minimum. So with this is a figure we extracted with this method, showing that if you use high repetition rate or some repetition rate, and you start going down with the repetition rate, while you are keeping your pump in CW, you get a huge amount of ASC at very low repetition rates. But as you start using pulse pumping technique, whether it's on one of the amps or two of the amps, you can really minimize this ASC down to very low levels. I will skip that, and I will skip that too because we are running out of time. And I will just show you that as the narrow band, as we use this technique with proper pulse pumping, with a very narrow band cedar and proper filtering, what you can get is a very clean signal, which A, has literally 0 ASE, and B, it has a very low level of nonlinearities, so you can minimize SRS like Raman by just proper filtering of the signal through the amplification chain. You can get up to 40 kilowatts with that, and you can imagine 40 kilowatts with 3 nanosecond pulse, you can get about 120 microjoules, which is it's not trivial. The pulse on demand, or what we call e-pulse, is really the method where the pulses can be kept with the to maintain the same energy while the repetition rate is being modulated. So this is just a demonstration to show how fixed or how stable those pulses are. This is what happens when you don't modulate it. But you can see that with this method, what you get is pretty much from 0 frequency, literally no pulses, to maximum frequency, you get literally 0 transition time. And this means that you can change your repetition rate to any repetition rate you want at any speed you want and still maintain a fixed amount of pulse energy. And just to conclude, this is just a series of images that are taken by using a camera with the LiDAR and getting those. So this is a 3D image. It looks like it's a 2D standard image, but it's not. It's a 3D image of I think it's Toronto. This is Barcelona. Again, it's the same kind of imagery where the 2 maps of the LiDAR, the 3D mapping and the camera, are being are layered one on top of the other. This is a very standard sort of imagery for vegetation areas. Power lines mapping, and mapping or modeling or planning of cities, of railroad areas. And this is a nice little gimmick that I wanted to show about the Mayan city of Tikal in Guatemala, which was just recently found. There were I think 70,000 buildings or ancient houses which were found, and they are undetectable with a camera because of the trees, and they were only detectable with the LiDAR by using multiple reflection algorithms. Another thing that was recently found in North England were ancient Mayan Roman roads, which were again undetected and completely changed the way that historians viewed that period of time and the population in these areas. This is an example of coastal line while doing flood control of cities. I think this is New Orleans. So just to conclude, we are still looking into the future, and into the future we have a lot of challenges, mostly the fact that this application is going for higher repetition rates, higher powers, shorter pulses, different designs like polarization maintaining designs, and it's all a huge challenge to see what will the next generation be like. So thank you very much, and I'm open for questions. Thank you very much.
Thank you very much, Doron, for the most interesting presentation. I believe that our audience understood everything in depth since they had the opportunity to watch your presentation several times, at least part of it. We have actually we face some technological changes, but now I believe that we overcome them. Anyhow, I would like to ask you about the example related to the buildings found in the Mayan city of Tikal using LiDAR detection. That was quite fascinating. And I would like to ask you, when referring to LiDAR scan beneath trees or vegetation, where do we have the main opportunities for improvement, taking into consideration the current LiDAR technology? Are they in the field of algorithms for data processing or in the LiDAR hardware development?
I guess it's both. I guess the challenge is on both sides. In order to really penetrate through the trees and get multiple reflections from the ground, the best thing to do is have more energy and to cover more ground, so that even if the pulse hits a branch, then a fraction of this pulse is being scattered back or reflected back. But the bigger the spot is, the more the larger the fraction that can penetrate eventually. So it's a combination of divergence and beam size, and then you got to have enough energy so that even a fraction of that energy is still being detected by the sensor. And then the algorithmic part is, I think it's working pretty well right now. You can get, I think it gets like a dozen reflections, and you can, but it is limited, because eventually you start getting something which is like aliasing. You get multiple reflections, and you don't know if these come from the original pulse or they are coming from a different pulse. You gotta know how to separate those pulses so that you literally you sense only the reflections that are generated by that specific pulse which you've shot. So I think it goes both ways, but it is quite amazing that things that are undetectable, whether they are really under the trees or in the jungle or even under the ground, and they can't really be detected. But when you scan through the area, you can find very subtle differences in the altitude, and then